we'll get started at about like 4:05, just so everyone has a chance to join in case people are having issues with the Zoom link or anything. Okay, so you all can see my screen, I assume. See my slides?
Yeah.
Okay. Yeah, so this is the Arduino programming workshop. So we're going to cover the basics of Arduino up through kind of code structures and how you would want to do certain things when you're programming like a robot specifically, and kind of how you can do that and not write tons of code. You can use libraries and kind of code structures that already have been written and developed and debugged and all that. So just kind of a preface. If you have questions, feel free, unmute, interrupt me, anything, post in the chat. I'll hopefully be watching that and can answer questions there. If not, just unmute, poke me, tell me there's a question, somebody, thank you. And then the recording is going to be posted, as well as the files I'm using are going to be posted and sent out in the newsletter after this. So you guys can look at those files afterwards if you want. And the slides will also be sent out if you want to look at that stuff after the fact too. So the preface, Arduino programming language is based in C and C++. That's what the Arduino language is. It's just C++ with some Arduino functionality built into it. And so you can either use this native C or C++ or do something like MicroPython or CircuitPython, which are implementations to use like regular Python code to run it on a microcontroller like an Arduino or an ESP32 or something like that. And they're not as fast as programming it in C, but you can do a lot more things much more easily in Python because it's a higher level language. So yeah, you can Google either of those two terms. There's like pre-built code that you upload onto a microcontroller, and then you can just plug it into your computer and drag and drop Python scripts onto it, and it'll do the rest for you. So it, like I mentioned, it's a lot slower, but there's a ton of libraries. As you know, if you've ever dealt with Python, there's a library for pretty much anything you could ever want to do, and that'll work on the microcontroller. Pretty much plug and play most of the time. There's some limitations on how much code you can upload because you don't have like a giant 10 gigabyte folder structure or something like you'd have if you're running on like a Raspberry Pi, but lets you do a lot more things much more easily. And then just in general, if you're having issues programming Arduino, Stack Overflow is your friend. Just anytime you have an issue, Stack Overflow has an answer. And then there's a ton of Arduino forums and stuff like that, which is more specific to like the Arduino Unos, Megas, stuff like that. You can get help there. And then in general, just regular C or C++ debugging and just Google searching the error, what might be causing this. And then, as I've mentioned a couple times before, I'm happy to help with figuring out things with your robot. So if you're having issues, can't figure out what this one error is, let me know. I'd be happy to look at it and give you a new perspective on what the problem might be. So the basics of Arduino programming, first thing, you have a setup function. The code that you put in this function runs once every time you turn the microcontroller on. So you use this to set up things like initializing libraries, start communication, and just general stuff that you want to do once on when you turn on the computer, sort of. So like your startup programs and Windows is basically what setup does. So it lets you kind of configure everything the way you want it to be configured. And then from there, you move on to like actually running your code that makes the robot do things. So some examples, you have serial.begin. So you start serial communication, mysensor.init. You initialize a sensor, something like this. All these things just happen once to kind of get everything ready to go. And then you can just keep using them repeatedly in a loop later. And then for configuring the hardware, you can do pin mode. So you give it your pin number. So like if you have an Arduino pin 12 or something like that, you want to say it's an output. Then that configures everything you need to tell the Arduino, I want this pin to be whatever voltage I tell it to be. It will be high, it will be low, whatever. You can also tell it you want it to be an input. So you want it to be able to read in voltages. You have to tell it pin mode input, stuff like that. And you can also set voltages. So if you have like an enable pin you need to control on boot, you can just in the setup function do a digital write the pin, write it high, which is 5 volts or 3 volts, whatever one, depending on which microcontroller you're using. And then that'll just always be on whenever the microcontroller is on. So like if your sensor had an enable pin and you don't care to turn it off ever, you can just say in the setup code, turn this enable on, and then just move on. So anybody have any questions about what the setup function does, how it works, what sorts of things you do inside of it, anything like that? Okay. And I'll, again, just if you have questions as I keep going through the slide, just poke me or send me in the chat and I'll be happy to answer it.
Wait,
so
is it necessary to set set it as an output or input? Like,
can you say that again?
Is it necessary to set the pin as an input or an output, or during your code if you just like just tell it to output like some voltages or whatever, like would that be enough, or do you need it initialized, I guess?
So the answer, as is probably expected, is it depends. Sometimes you don't need to tell it, I want this to be an output. Sometimes you don't need to say it needs to be an input. It just depends on what microcontroller you're using specifically. So I'm pretty sure for all the Arduino, like AT Mega, Arduino Uno, Arduino Nano, all that stuff, I think the default is to set the pin as an input. So if you're trying to just read a voltage, you don't need to say pin mode input. But if you're trying to use it as an output, I think for the AT Mega, all the Arduino, really 8-bit basic Arduinos, you need to tell it you want it to be an output for you to be able to actually drive it and control what voltage. But for the input, you don't necessarily need to, but it's generally kind of best practice to say, is this an input or an output for every single pin, just in case for some reason something is weird or you decide, oh, we need to switch to like a slightly different microcontroller. It should just transfer over with you changing the pin number and it should be fine. If you tell it input or output, if you assume like the default works, it may or may not work if you just copy your code over. So best practice, but not always required. I would just recommend generally describing it, but like you don't need to do it for every single pin, just ones you want to be like a logic 0 or a 1, 5 volts, 3 volts, 0 volts, whatever it is. But if you're doing like communication, the pins for like I2C or for serial, you don't need to tell it. There's no like pin mode serial or something. You only use this pin mode function when you're actually like driving like a digital voltage line. So like an enable pin or something to like where you'd send out a 0 or a 1 voltage, not like something you'd send like actual data over some sort of communication protocol. Does that make sense? Kind of went off on a bit of a tangent.
But... Yeah, no, yeah.
Okay.
Makes sense. Thanks.
Anybody else have any questions? Should we move on to loop? Okay, so yeah, so once the setup function runs once you turn on the microcontroller, after it finishes, it calls loop, and that function just keeps looping around. So once it finishes all the code in the function, it jumps back to the top of the function and just keeps kind of cycling down all the code there. So it runs over and over in a loop. And in this function, you're basically monitoring everything about the microcontroller. You're reading in like battery voltage, or you're setting your motor speed, whatever you want to do in there. And you just want to make sure everything is up to date with whatever current control signals you have or inputs you have, whatever it might be. So some things you might do here is if you digital read, which just takes a pin that you set as an input, it takes the pin if it's like 3.3 volts or 5 volts, if you're using like, depending which microcontroller you're using, if it's a logic high voltage, you'll run some sort of code, and then you can do else. If it's low, do some other bits of code. I'll have some examples a bit later on for all this, but you can kind of determine like, if this sensor says, oh, there's a green ball in front of it, I want to run this code, like I want it to fall into this ball storage container. If it's low, I want to fall in that ball storage container. And so you can kind of determine where like a servo moves to direct the ball or things like that. And if you have like a library that has like this color sensor in it, maybe that is like you communicate with more, so like it tells you like an actual RGB value or something, you might need to do mysensor.update to like let the code kind of update the sensor to make sure it has the latest information about the sensor. The sensor is like up to date with what configuration you want it to have and stuff like that. So things that you want to kind of keep happening and kind of keep data in sync between your sensors and your main microcontroller. And then, as I was kind of mentioning, you can do in setup, you can do a digital write here. So if perhaps in this first example, if digital read, the pin is high, you want to turn a motor on or something, you can do inside of that if statement, you can say digital write this motor pin high, that'll turn your motor on. And then when the digital pin that you're reading from a color sensor or something is no longer high, you can have it turn off the motor. So you can kind of control these outputs based on your inputs, and you can keep doing this in loops over and over. So whenever the color sensor goes high, you immediately make sure your motor goes low or high or whatever you want to do. And with whatever kind of steps you want to do, you can make it wait like 30 milliseconds after it goes high. You can make your motor turn on or off, and basically anything you really need to do for the mechanics of your robot and how you want your code to work. So does anyone have any questions about how loop works, what you use it for, anything like that? Like I mentioned, also more examples of all this kind of later in the slides. Okay. So the main reference that you're going to need for basically any Arduino programming is just Arduino's website. So the link is there. You can also just Google Arduino reference and it'll come up, probably the first result. And so I've kind of listed out the main kind of functions you'd need for pretty much any general robot program. So in your setup function, or in setting up your robot, which would happen in the setup function, you'd want to use pin mode to tell it. And before I continue, all of these functions are described in the reference I just mentioned. So like there's a whole page about each of these describing what they do, how they work. So if you want more information about any of those, please go there and it'll have more information. But like when you're setting up your robot, you can tell what pins you want to be inputs, outputs, if you want them to be pulled up to logic high or pulled down to logic low, whatever. You can do things like attaching and detaching interrupts, which are basically a way for the microcontroller to automatically run some bit of code immediately whenever some sort of event happens. So like if your color sensor, if it like changed from a low voltage, like no ball detected, to a high voltage because there's a ball detected, if you have an interrupt attached to the pin that the sensor is connected to, without you writing any other code, as soon as it goes high, it can call a function that like happens whenever the sensor says there's a ball here. So you could have like a counter. So you can say how many balls have gone through here. As soon as the pin goes high, count up. And then once it goes low again, you're ready to count the next ball or something like that. So you can do that all with interrupts, using attach interrupt or detach interrupt to start watching for the interrupt and to stop watching for the interrupt. So like stop watching for the balls coming or start watching for the balls coming, whatever you'd want that to be. And this can apply to pretty much anything you'd want, not just a color sensor. You can have it for communication too, if you want. You can do all sorts of things. But yeah, so interrupts are a bit more advanced, and I can go in more detail one-on-one. If anybody wants to use that in their robot or having issues with it, let me know. And then so for kind of taking input to your Arduino code, you have digital read and analog read. So digital read is on, I believe, any pin of the Arduinos generally. and it just tells you, is this voltage a high or a low? And like I mentioned in the reference document linked there, it tells you like exactly, I think, the voltage that it cuts off at. So low is technically, I think, 0 to like 0.7 volts or something like that. Don't quote me on the number, depending on if it's a 5-volt Arduino or a 3.3-volt Arduino, kind of varies. But basically, digital read is going to say it's a 0 or a 1, and it kind of ignores whatever actual value it is. So it could be like 2.3 volts, and it'll say, oh, this is high. And if it's 5 volts, it could say, oh, this is high. So you kind of get, is the sensor on or off in that case? But you can do that in pretty much any pin, I believe, after doing the pin mode input or in pin mode input pull up, whatever you want that to be. And then you can have analog read, which will actually give you the analog voltage from like 0 to 1024, 0 to 255, which is just from 0 volts in little increments up to 255 is the same as 0 volts all the way up to 5 volts. So you can get the actual analog voltage that was at that pin, but this is only on certain pins of the microcontroller. So on the Arduino, I think there's like 7 or 8 pins on an Arduino Uno. There's more on a Mega, less on a Nano, but you basically can read actual analog voltages there rather than just, is it a low or a high, 0 or a 1? And so you'd want to use that if you're doing something like a ultrasonic range sensor or something like that, that gives you a voltage output. You can use the analog read to tell you about where is the voltage output, which is about how far away is the wall or whatever you're driving around. Okay. And then the next input thing that you would really deal with is pulse in, which is when you're dealing with a PWM signal. So some sensors output a PWM, and you can use pulse in to basically give you a value of how like large the pulse is, I guess. So it's a bit complicated because it gets into how the PWM is constructed and all that, but it's all referenced in the reference material. So feel free to read that if you need to use that, but this is a more niche thing. It's more used if you're working with like off-the-shelf radio transmitters, or if you're working with like very specific sensors. Most of them use other sorts of communication. So honestly, you probably don't need pulse in, but I just wanted to mention it. And if you guys think you might need to use it, let me know. I can help explain it a bit more in detail. And then, so kind of the siblings, I guess, of digital read and analog read are digital write and analog write, which instead of reading in a 0 or 1 or reading in an analog voltage, it can actually write out a 0 or a 1. So it's going to pull the voltage to ground, pull the voltage to 5 volts for a digital write. And an analog write, you can say, I want it to be like value like 128, which is right in the middle of 0 to 255. So it'll give you right in the middle of 0 to 5 volts. So you get about 2.5 volts on the output. So they kind of work in the same way, but instead of intaking data, they output a voltage. So you can use that again to control microcontrollers, to control like how far a motor rotates or how quickly it rotates, whatever it might be. And then sort of timing is the last section I'm going to go over here. And basically this is how you determine how fast your code runs and like how long your code has been running for. So the delay and delay microseconds commands will, when they hit that line of code, they will stop for however many milliseconds you say, which is the delay function, or stop for however many microseconds the microseconds command says for it to stop, and then it'll start moving on. So if you want to say, I want to turn my motor on, I want to wait 30 milliseconds, and then I want to turn it off, you can do that. Digital write high delay for 30 milliseconds, and then digital write low, and that'll run it for 30 milliseconds and then turn it off. And then what the millis and microseconds functions do is they give you basically a number of milliseconds or microseconds since the microcontroller turned on. So you can use this, and again, there's an example a bit later of like, I want this code to run every 10 milliseconds. So you can kind of watch the milliseconds as this function keeps returning them. And then after it hits 10 milliseconds, you can run the code, and then you wait for another 10 milliseconds according to the function. And that kind of lets you loop and do things over and over, but not every single time the function loops. You can make it happen kind of a bit slower, because you may want to be reading in this digital signal at as fast as you can, but you really only need to send data over your serial connection at like a couple characters per second, maybe, I don't know. So you want to kind of be able to control how fast each of those things run, rather than saying everything is going to run as fast as it can no matter what, because you waste a lot of resources and time when you do things like that with Arduinos, because they're very low power and low CPU power intensive. So anybody have any questions about those before I get on? And again, the reference is there if you want a bit more detail about any of them in particular when you're actually working with them. Okay. So next, you have kind of your flow of how your code is going to work. So you have control things and you have loops, are basically all the ones you really have or need in Arduinos. So you have if else statements. You can see the structure on the right in my wonderful dark mode IDE. So basically this lets you check different conditions like I mentioned in the previous slide. So like if a pin is high, I want to run this bit of code. If the pin is low, I want to run this bit of code, whatever. So you can put things in between the curly braces, and that code will run if the condition is met. So if X is true, then the first line of code here can run. That's a very bad color. Let me change that. So if X is true, this code will run. And if X is not true, but Y is true, then this code will run. And if X is not true and Y is not true, then this bit of code will run, is basically how the if statement generally works. So you can leave out the else if part, you can leave out basically any part of it you want. So you can just end all of this. You can leave all of this out if you just want it to be, if a pin is high, I want to increase a counter, or I want to send a character over serial to the Raspberry Pi or something. And then you can do, if the pin is high, I want to send a voltage out through analog write. If it's not high, I want to do something else. You can leave whatever pieces of this out that you really want to kind of get whatever logical functionality you want. Okay. And then in terms of the loops you can do, there are a couple options, while and do while. You don't really need to use do while ever. It doesn't ever really come in handy in robotics, at least in my experience. You can do everything with the just simple while loop, which is this one on the left here. So the while loop, it checks this condition. So if Z is true, it runs this loop. If Z is false, it just skips by everything and just goes directly from here all the way past it and just ignores whatever code was in the middle because Z was false. The difference for do while is it always runs the code in the middle. So it comes in, it runs this code, and then it checks this condition. So if Z is false, it'll still run the code in the middle. So really the only difference is do while runs the code in the middle at least once for sure. The regular while loop runs it some amount of times. It doesn't guarantee you'll run it once or you'll run it twice or anything like that. It just, if the condition is met, it'll run it. If not, it'll just move on to the next piece. And then the last one is the for loop, which lets you run code a number of times. So this number can be hard coded, so you can see you can have it run for n times, you can have it run for 3 times, you can have it run indefinitely, you can just say, I want this to run forever, and then you just leave out this piece. I guess you could really leave out everything and just do semicolon, semicolon, and you can run forever. There's a bunch of different things the for loop can do. You can have, say, I want to do this up until, like, say n, just say this is like, I don't know, like get a sensor value I want to run up for the 12 sensor samples I have or something like that. You can make it adapt in real time to however many loops you need to do, or you can have it hard coded, or you can have it run infinitely. Really, you can do pretty much anything with a for loop that you'd want. So does anyone have any questions about either of these two kind of code structures you might see?
So the while loop repeats the do part, right? The do while.
Yeah, so the way, let me see if I can change color to make this a bit more readable. So
I can read it. I just mean like, so I'm saying that the while loop or the do while, it repeats the entire do part, right? Every time.
yes,
Okay.
yeah, so
It
the
just
only,
says,
the only difference between these two is that this one runs the code in the middle at least once, and otherwise they're exactly the same. Like if you do like this is very hard. If you do I++,
yeah.
so this one will do it however many times until Z is false, and this one on the right will do it however many times until Z is false plus 1, because it always runs it to begin with, and then it checks the condition, and if the condition is true, it jumps back to the beginning and then loops and does the I++ thing again. Does that make sense?
Yep, thanks.
Okay. Anybody else have any other questions? Okay. So using the Arduino IDE to upload your code to an Arduino. So obviously you need to download the Arduino IDE. The link is there. Also, you can Google it. It's on the front page of their Arduino website. So you just get that downloaded, installed, write your code in the IDE, and then these are the settings you have to go through. So you have to set the board. So you can see over in the tools dropdown, there's this board option. You just have to use the dropdown to select whatever board you're using. So it might be an Arduino Uno, an Arduino Mega, could be an ESP32 like I have here. And so once you do that, you configure your board specific settings. So all of these are for the ESP32 specifically. If you have an Arduino Mega, I don't even know if there are options. So all these options here are kind of specific to whatever board you're working with, and there might not even be any. So the defaults generally work, but if you're having issues, I can help you figure this out. And there's tons of resources online where like what people recommend for these settings, depending on which board you have in particular. And then you set the port here, which is what serial communication port your computer is connected to your Arduino with. You can set the programmer. Generally, this AVR ISP Mark II works perfectly fine for pretty much any Arduino I've ever seen. You can change that if you want to use something other than like a USB programmer. You can use like an AVR, like a non-Mark II ISP. You can use like an ICE programmer. You can do, there's a ton of different options, but the default one works fine for pretty much any like off-the-shelf Arduino you can get. And then after you do that, you can just click this upload button here, which is just the arrow, and then we'll compile your code. It'll tell you if there's any compile errors, and if it compiled fine, it'll start uploading to your board. And so kind of just a quick procedure to figure out which port you're on. So depending on if you have like a legitimate Arduino board or if it's a third-party made board, it may or may not show in the port. It says like a port number, and then sometimes it shows parentheses like Arduino Mega or something like that. But if it doesn't, you can just open this tools drop down, look at what ports are available. Maybe there's like 1 and 7 that are available. then plug in your microcontroller over USB, then click on tools and see port. And then there's a new one, which is like, then 9 shows up in this list. And then obviously the new option is the microcontroller you just plugged in. So just select that one and you should be good to upload. Anybody have any questions about kind of how you work with the Arduino IDE to upload? Okay. And again, like I'm going to say way too many times during this presentation, if you guys have issues uploading, Arduino can be weird and the error messages are kind of terrible and they're hidden basically in the bottom of the IDE. Let me know. I've dealt with so many Arduino issues, I can probably figure out what's going wrong with your upload. So just shoot me a message on Discord if you're trying to program your robot and it's just like, no. So we can get onto some more complex Arduino code structures, I'm calling them. They're kind of similar things you might see in like Arduino code. So there's some things like I mentioned earlier, make code run at about 10 times per second. You can use header files to control values and all sorts of things like this. So it's not like a full example of like, of PackBot code or anything, but these are kind of the structures you might see copied and pasted and changed a little bit in real robot code. So let me get these downloaded and then I can open them up and show you guys. But while we're waiting for that, so the examples I'm going to go over are listed here. So I guess I have like 4 examples I'm going to show you actually. So the logging. So if you want your code to run at about 10 times per second, say you want to check your sensor value kind of slowly because you don't really care how quickly it updates. You just want to know, is there a ball in the launch chamber? You don't need to know immediately when it happens. You just want to know about when so that you can run your other code. Because if you want everything to run as fast as possible, you need a lot of CPU resources and your microcontroller needs to run really fast. And that's kind of a tall order for microcontroller because they're not really meant to run super fast. They don't run at gigahertz or anything like your CPU in your computer. They run at like super fast ones run at like 400 megahertz. It's like, I think Arduinos run at like 8 megahertz, like the Arduino Nano and Uno and Mega run really slowly. So the more things you can have happen slowly, basically the better off you'll be with putting in more code and more things your Arduino can do. So that's one way you can do that. And like I mentioned a little bit earlier, you can use a header file to control code behavior values. So say you want to wait 30 seconds after you detect a ball in your ball launcher before you launch it. You can say in your code, like on line 372 or something, you can say delay 30 and then launch your ball or whatever. So you can do that, but if you have to change the value of how long you want your ball to sit there before it kind of stops wiggling around and gets ready to launch, it's kind of annoying, especially if you use it more places than one, to go and like Control F and try to find which ones are actually 30 milliseconds. And if you forget to change one time, now you have one that's like 30, one is like 20. It gets really messy. So you can use a header file to say, here's a value that I want to like configure. And you can say like ball resting time milliseconds and say 30. And then in your code, you can just use that kind of variable thing, copy and paste it everywhere you need to. And when you want to change how long it rests there before it launches, you can just change one number in the header file, like 20 or 40 or whatever you want it to be. And it'll update everywhere else perfectly without you needing to go Control Fing everywhere. And on kind of a similar note, you can use a header file. You can also use a header file with custom libraries to organize code and make more readable. So you can have like a class that is, let me get this set up before I try to keep talking. People have questions, feel free to shoot them out now while I'm trying to get this set up. Okay. Okay, so yeah, you can have custom libraries which will let you have your own custom objects in code. So you can say, I'm going to write all the code for dealing with my motor driver in this one file and everything. And I can just say motor driver dot spin at a set velocity or something like that. And I don't need to worry about digital writing with the right PWM values, and they need delays you need to have in there. You can kind of just make it really easy to read your code because it's just motor one dot set spin or set velocity, and you don't need to worry about how it actually happens. You can just really easily read it and see like what is actually happening without needing to be like, well, lines 20 through 32 are just for setting the motor speed to this speed. And then you do the same thing again for a different speed or a different motor. And then you also have to write the code over and over and over, which is just too many things to type out and hard to read. So like, why would you want to do more work? So custom libraries can help you kind of write the code once and then reuse it for a bunch of different things. And then the last one I'm going to go over also exists in a header file, is a custom structures or unions. This lets you put a bunch of data kind of packed together. So you can say, if you want to use EEPROM to store data between, like store configuration data for your robot. So say you have like an offset for your motor, your motor ideally would turn on when it goes high or to like 2.3 volts or something, but actually you need to go up to 2.4 for one. It needs to go up to 2.6 for another one, something like that. Those values you might want to store in your Arduino so that whenever you program it again or turn on the Arduino, it's already ready and has that all, so that they'll all turn on at the same time. You can put all these little offset little numbers all packaged together in one structure that's like motor 1 offset, motor 2 offset, motor 3 offset. And then you can take that whole thing and just write that to your EEPROM or storage that exists on the microcontroller. And then whenever you want to read it out, you just read it into the structure. And then you can say, what is motor 1's value, motor 2 value, motor 3 value. You can just really easily read it out rather than saying, at this address, there's this number, and then at this other address, there's another number, and at this other address, there's another number. And it kind of comes back to the thing of custom libraries. Like, you don't want to write code over and over and over to do things. It's a lot easier to just write it once and it for just work and kind of all be written in one place and reuse it as much as you can. And then finally, yeah, go ahead. Somebody say something. Apparently that was somebody outside my apartment. Anyway, so last thing you can do is manually setting registers to control pins. So if you're trying to do like a really fast pulse of a pin from 0 volts to high to 0 volts, like 1 microsecond long or something like that, you can do that in another Arduino. It's more complicated because you can't do digital write, delay 1 microsecond digital write, because digital write takes like a couple microseconds to actually do, because it's checking a bunch of things to make sure everything is set up and then it does the write. So you can bypass this if you really need to. You'd be like manually editing the microcontroller registers to say, turn this pin on high, turn it off. So if you really need to do this, let me know. I can help you figure it out. But if you can, it's better to avoid this because it makes your code harder to read, because it's just like register names, which are not really clear. It's like all caps and it's like 30 characters long to describe like a register. And then you're doing bitwise operations to set a single bit in it. And it's just kind of tricky to do and kind of confusing to see what's going on unless you actually are familiar with it. So that's an option if you need to send out quick pulses or things like that, but avoiding it if possible would be your best bet, I think. Okay, so we can move on to the actual examples here. So I'm in VS Code. So here is everyone can see VS Code, right?
Yeah.
Okay. Can people read the text, or is my settings too small? Okay, there. So this is one code structure you might find to run code at a certain frequency. So here, basically, you have your setup, like I talked about. You have your loop, which runs this code. Once it finishes, it goes back to line 14, runs your code back to line 14, runs your code back to line 14, over and over forever until you turn off the power to the Arduino. So what this is doing is every 10, or so it's trying to run this code here at 10 times per second. And so the way it accomplishes this, the calculations are up at the top. So you can say, I want you to run at 10 Hertz. And then you need to calculate how long each period between runnings is. So there's 1 second divided by 10 times per second gives you 100 milliseconds. Actually, I just realized I missed that. So this is 1,000 milliseconds divided by 10 will give you 100 milliseconds between running your code. So every 100 milliseconds it needs to run it. So the way this is done is it's using this milliseconds here on line 14 and says, what's the current time basically? Is this greater than the last time we ran this code plus this 100 milliseconds between times we run it? So to start off with, we're running it. Last time was at 0. You basically just need to say, we've never ran this before, so as early as you can, the smallest value you can have is 0, because unsigned means there's no negative sign, so smallest is 0. So if 0 plus 100 milliseconds, if our current time is greater than that, we need to run our code, but we also need to say what's the last time we ran this code is basically like now, is milliseconds. So next time we loop around, milliseconds might be like 101, but we just ran it at 100, and there's another 100 milliseconds for the period. So this is false, so we don't run it. We just check the condition and then move on to our other code here. And then until this comes to be like millis is, I don't know, maybe it's like 204 because some code down here on line 21 took a really long time to run or something. The last time we ran this was at 100, and it runs every 100 milliseconds like it calculates here. So if this is true, we update the last time we ran to be this 204, and then we run our code to do whatever communication over serial, whatever we want it to do. And then the next time it comes around, this value is this last runtime 204. That's false. And so we just kind of keep going around doing our other things. So does that make sense to everyone, kind of how that works? Or rather, what questions do you have about this kind of code? Okay. So yeah, again, also if people have questions after the fact or people watching the recording, shoot me a message on Discord if you'd rather me like go over stuff one-on-one. I'd be happy to do that. Like, no worries either way. So this is how you make code run at some sort of frequency slower, because if you didn't have this, if you just ran like this would be running at like maybe that many times per second. And if you need to send serial that quickly, like you're going to use so much of your processing time just for dealing with things you really don't need to deal with, that the important things that need to run super fast aren't going to have enough processing time to actually happen. So
Wait,
that's
if it's all in the big loop, then how would you make some things run quicker and some things not run quicker?
Yeah, so basically this line 14 to 19 makes it so that lines like 18 to, I guess, 15. So these highlighted lines run at about 10 Hertz, but the code down here, like on line 21, this will run at like 10,000 Hertz or something, because this condition is only true 10 times a second. And so this will only run 10 times every second, but this is going to keep running over and over because this loop function, once it gets to the end here after like 0.1 milliseconds or something like that, it'll come back up to the top. It'll be here.
Gotcha. That makes sense. So it just skips over that code and saves processing power.
Yeah. So
okay.
So most of the time, this is just, this condition is false. And so basically what happens is it just ignores that this exists. And then it just looks like this. This is actually the code that runs most of the time. So like if you imagine this is your like super important fast code, I guess I++ is very important. So if you want this code to run really fast, you can. And then you can also have your less important things like, you know, controlling your robot. You can have that run at 10 hertz, but your favorite variable I can be going up very quickly. So
would you say that the serial is considered super important, or?
So not necessarily. I'll get into a bit more why serial isn't super important. So a bit later, but what you can do is you can have multiple of these. So you just have to like change these variable names, and you can say this one will run at like 50 hertz or something. Like this is like a little bit more important. This is less important. So you can do this for a bunch of different things. So you can say like maybe communication would run at 50 hertz. You'd like see, is there a new command ready to go? We'll check 50 times a second. We want to do like, I don't know, here maybe you'd put like kinematics equations. Like, so if you're trying to figure out where, like how the robot arm is oriented or something, you might want to calculate that really quickly over and over or something for some reason. And you might be looking for, is there a new command ready to go every 50 or 50 times a second, whatever. And you might check your battery voltage like 10 times a second because that doesn't change very quickly. So you might want to check that a little bit slower. Your communication might be a bit more important. And then your like super high important stuff is like dealing with where you are and where your motors need to be and all that stuff. Does that make sense?
Yep, thank you.
Okay. Anyone have any other questions about this run at hertz frequency stuff?
Quick question. So if outside of your like if statement, if you had like sleep for 1 second, then the if statement wouldn't run at 10 hertz, right?
Yeah. So if you did a delay, which is like stop here for 1 millisecond. So that's why in the slides I said about 10 times per second, because yeah, you're exactly right. This is only true if your microcontroller is fast enough and you're not doing things like this, because it doesn't guarantee it will run at 10 times per second. It's going to run at up to 10 times per second. So if you do have something like a really long, like say you wanted to, if you had like a if digital read of sensor, comma. So if you did this for some reason, like if a pin is high, you want to wait for 10 milliseconds before you do something, like, yeah, that's going to stop this or at least delay it. So it's going to be running at like 9.8 times per second or something like that. So when you're doing this, you want to make sure you're aware of how this is working, and like your loop needs to loop fast enough so that it can check this condition, because if it's waiting just kind of stuck there for 100 milliseconds, it will not check this condition and this code won't run. It'll get delayed because you're delaying all your code when you call delay here. And I'll go into a bit more detail on how you kind of avoid that issue in a little bit once we start talking about the next topic after these example structures. Okay. Anybody else have any other questions? Okay, then I'll move on to the next one. So this is a header file, like I mentioned, you can use it to control code behavior or values. So my example of waiting for 30 milliseconds before you launch a ball after you detect it. So what you can do in C++ is use this define preprocessor instruction. It's basically a way for you to tell the compiler, whether that's Arduino or VS Code, whatever you're using, you can say, I want to do like ball launch delay. Also, just a side note, I use all caps for the defines because they're not actually variables, but they look like them in your code. So I just use all caps to kind of differentiate what is a variable and what is like these predefined values. So so you can add things like this. So the way this works is basically if you have this in your code, ball launch delay anywhere, you can say like, should have kept that there. So you can do like delay for ball launch delay and then digital write. And then just for clarity, so you can do something like this. So if you have a digital read, if your sensor says, hi, there's a ball there, I want to delay for ball launch delay milliseconds, and then I want to write my output hi. So what this actually does when you have a define like this, it copies this value, like literally copy and pastes wherever it sees this text ball launch delay. So it does this. And obviously the extra parentheses don't really matter. Best practice is to put parentheses in case you're doing multiplication or something like that, where if you do like ball launch delay 30 plus times 2, the way order of operations can get weird depending on how complicated this gets, because you can put like math in here. You can do like 30 divide by 4.0, and then you can do plus like, I don't know, you can do another one inside here, which is like, so it gets really complicated. So best practice is whenever you're writing these, put parentheses around it just to make sure your math works the way you intend it to work when it literally just copies and pastes it wherever. So, and then whenever you want to say, okay, actually it needs to settle for 40 milliseconds, you just change in this file 40. And then whenever you compile it next, anytime you say, I want to delay for 40 millisecond or ball launch delay milliseconds, it'll update to the new value. So if you had it here, if you had it in another file, whatever it might be, it'll all be based on this single number. So it's really easy to change it. And also when you're reading the code, it's much easier to see why are they delaying for 40 milliseconds? Oh, it's because the ball launch delay, something like that. And you can do this for all sorts of things. You can have just integers like 40. You can do like floating point numbers with a decimal. You can do all sorts of different things. You can say, what's your sensor address? What's the pin number of like this like motor output? What's the pin of this sensor input, whatever it might be. You can put this here, and then you can just say, instead of saying pin mode output, because maybe you want to change which pin is plugged into, maybe you broke that one pin for some reason, you can just say, well, I'm just going to change it. It's not plugged into 4 anymore. It's plugged into 7 or something. And then everywhere else, it'll all be ready to go, basically. And then, so kind of a common structural thing you'll see in these header files, which are basically, header files don't have code in them. They have things that describe how the code is structured. So this is just you talking to the compiler, basically saying, these are all the things I want you to do to my code before you actually compile it, sort of. It's more complicated, but this is not a compiler lecture, so I'm not going to get into that depth. But you have this if not def header file H, define header file H, and then an ndif at the end, just because when you're including files, so you do something like include header file.h, you do this. If you have another file that also is like uses this ball launch delay number, if you include it twice, it will define it twice, which gives you compiler errors and warnings and stuff. So if you say, if it's not defined, do this, but also define this thing. So the next time if another file includes it, this is already defined. If not def, no. If it's not defined, but it's already defined, so this is false. So we don't include any of this. This just all goes away. But really all you just need to know is you need if ndef and then something. I normally do the whole name underscore H, define the exact same thing, copy paste, and then at the end, ndif. And again, all these files will be up on the website and the links will be sent out. So you guys can kind of look at them and see, why is my code not working? Also, again, like I mentioned, I'd be happy to help point out things. So anybody have questions about how header files work in general? Okay, guess we'll move on. So we're going to start off with another header file. You can see the same if ndef simple underscore H, define simple underscore H, and then the ndef at the end. And so this is talking about the custom libraries organizing code to make it more readable. So this is a very simple example given the name. So this is a common C and C++ thing. There's tons of tutorials online to learn more. And you can just copy paste this, change the structure for your own code if you want. But basically this lets you create a simple object, which lets you call these functions and have values, so that maybe setting a value is really complicated. You can just put all the code in one place, and then you don't ever have to like rewrite the code. You just change it to one place and it fixes everywhere else if there's any bugs or anything like that. So I don't want to get too in-depth in what classes are because they're fairly complicated. But basically, it's a way of wrapping your code and kind of putting it all in one place to make your code more readable. So here you have your main function, which has your setup and your loop. And like I mentioned in setup, you might need to do a .init function. So you have your object, which is a simple thing, like it mentions here, as the name matches. We're creating a my object is the name. We initialize it here in setup on boot. And then every time we loop through, we set the value to whatever your value is, whatever that might be. And then you can get the value back, whatever. This is a very basic and kind of doesn't really do anything code, but it's just kind of a way to see, like maybe set value is a really complicated thing. It has to do like really complicated matrices math or something like that. And like if you wrote it out, it would make your code so long. But actually you can just put it in one place and then it's like, yeah, one line of code does all of that and you don't need to worry about it. And it's really easy to see like, okay, so this is just setting the value. How it does it, I don't care. I'm just doing the things that like I logically need to do for the robot to work. So does this sort of thing make sense? Again, like a lot of these things, I can go over more in depth if you guys actually need to implement them in a robot. I just kind of wanted to kind of bring them to your attention so that you can think about using them in your robot, because if you don't know about them, you're not going to think to use them. But if you've seen them once, I feel like you'd get a better sense of, hey, we could use that thing that Eric talked about. I don't know what it is, but the answer to that or the solution to that is just sending me a message, and I'd be happy to go more in depth and explain how it might work, or there might be something better that I didn't think to mention in the slides. So anybody have questions? Okay. Yeah, so if you want a bit more of an interesting example, I have the PackBot code. It's kind of a lot. So you can see all the defined statements we have here for PackBot, controlling everything from like wheel diameters to like how much voltage we want to be able to apply to determine how much torque and current we get into our motors, the tuning parameters we have for position, velocity, battery voltage limits we have. All of that is just here. And if we want to change it, we just change it in one place, fixes everything. And like I mentioned, you can do like math here too. So you can have like macros to convert things rather than like having an actual function to do it. But that's another topic. And so you can see we have an object which has a ton of different things it does, which kind of a bit much. I don't want to go into it too much, but basically we can say like set the position, set the trajectory, and then if you go into the code, it's very long and very annoying to read through. And imagine if like you wanted to tell it to move to this position and you had to write all of this code every single time you wanted to move to a position. But actually all you have to do in PackBot code is just do motor.setPosition and then you forget about it. It does everything else for you. You just give it a number and it does all the other code automatically. Just you write it once and then your main loop is really, really simple. You can just say like motor.setPosition 20 millimeters or something. It lets you make your code a lot more readable and kind of put your code in different files to kind of organize things to make it easier to work around and debug and stuff like that. So last thing I wanted to show you some code for is a structure. And again, there's the if not defined structs H defined structs H thing to make sure it only gets defined once. And so this just lets you put multiple values next to each other basically in memory. So you can say the sensor struct has an ID, a value, and maybe it is a pointer to your, it holds the address of the next one. This is again, more complicated stuff, but what you can do is if you have like sensor struct TS, and I can't do that in here because it's not a .h file. Anyway, so ignore that it's going to give me compiler warnings, but what you can do when you have a struct like this is you can do s.sensor ID equals like 3 maybe. And then you can say s.sensor value equals like 20 or something like that. And then whenever you want to read it out, if you have this s object, you just do s.sensor ID or value, whatever you want to do. And you don't need to like keep track of all these values separately. They can all be really easily accessible like this. And when you want to say in the example of having motor offsets, you can have like maybe we'll just change this to be an offset here. And so on, so like it does that. And then if you want to maybe save this to EEPROM, you can just do EEPROM.write, and then you can just give it your struct, and it will figure out how to pack this all, or it'll copy that into the EEPROM, which is just a place to store numbers. Even if you lose power or you reboot the robot, it'll still be there. And it's just really easy to save, say, .write this structure, and then it'll write all of these values. And when you want to read it, you just do EEPROM.read. Can't write. And then you can just do read, and then you get like, I don't know, T equals. And then you can do T.sensor offset 1 or something like that. And you don't need to read every single value out individually. And it's really easy to pass values around using this sort of structure. I'm taking a little bit of liberty with the read and write. You need to do a little bit more wrapping to make it work with a structure. But again, if you need or think you want to try to use this, let me know. I can help you walk through actually writing the code for it. Okay, so anyone have questions about this before we move on to the next thing? Okay. Okay, so let's move on here. So upon recommendation from Kurt, and because Arduino IDE is a bit finicky and weird, but if you want to still use it, you can organize your code to have different tabs. So normally you have all one file, which has everything in it, but you can use this drop-down arrow on the right to add a tab which has more code in it. So basically, the normal way it works is using the pound include or hashtag include thing, like you saw in the other code, tells the compiler what files you need. Arduino doesn't do this. You don't need to worry about it if you're using Arduino IDE. But the way it actually works in Arduino is each tab is just copied all into one file and then it's compiled, which has some weirdness to it, I'll say. And I'll go into that in a bit here, but this lets you organize your code a bit more. So you can have like your first tab can be like you're setting all these values, your defines, you're saying, I want to wait 30 milliseconds after detecting a ball before launching. I want to say the I2C address of this sensor is this value, kind of setting values like that. Your next tab can be all of your code for controlling your different motors. Your next tab can be like the loop function, which has everything running in a loop, something like that. And so you can kind of organize your code that way so it's a bit easier to read and figure out where things might be. So the way this actually works is if you see I have tab 1, 2, 3, they each have their own bit of code in them. And the way this literally works is Arduino just copies and pastes those lines of text all into one big file. So you can see num at the top, tab 1 function, then there's tab 2 function, and then there's setup and loop. So it just copies all of that and then compiles the version on the right. So what does it mean? You can reference any variable anywhere in any tab. So you can see here num is like defined on line 1, integer number equals 0. And then on tab 2, it says num equals num plus 1. So there is no num on tab 2, but it knows about it because it is on tab 1. So you can kind of reference things that way, and they don't need to be right next to it, which is a little bit harder to read in my opinion, but it's something you can do if you want to organize your code that way. And then just something to warn about that. So if you're not aware of all the names everywhere, if you give things the same name accidentally, it'll just break everything because two things will have the same name and just your code will not work correctly. It'll probably compile, but it will not like anything at all. It will be very weird and debugging is very painful. Yeah. And so the order of code and variables is very important. So if the tabs are ordered tab 2, tab 1, tab 3, that'll give you an issue. So the issue is that this int num line will be put down, maybe say on like line 7, but tab 2 function will be on line 1. So on line 2, it says num equals num plus 1. But the way the compiler reads down line by line, it gets to line 2 and says, what is num? I have no idea what num is. Nobody's told me what num is. And then it gives you an error and says, no, I'm not compiling. Even though if it were to look on like line 7 or whatever, it says int num equals 0, then it would know. That's not how C and C++ work. It has to be defined first. You need the variable num. So yeah, it says not declared in the scope because all of your integers and numbers and all that stuff have to be defined, and then you can use it later. You can't ever use it before defining it because it's like, I have no idea where that number is, what you're talking about. It means nothing to me. And then just gives up and crashes and says, compile error. So some ways to fix this sort of issue is you can prototype functions and declare all global variables in the first tab. So you can see here on tab 2, I have integer number is defined or declared. So there's int num So then when it's reading line by line, the compiler sees, okay, this is where int number is. Here's all of my functions, tab 2, tab 1, setup loop. So it knows about all of the things it needs to know about. So when it gets to tab 2, it's like, okay, here's the code for tab 2. It uses num. I know where that is. That's on line 1. And then when it gets to tab 1 over here, it says num. Oh, I know what num is. I'm going to set that value to 0. And then it does that, and then so on and so forth. It's able to kind of keep track. Since it knows that they exist somewhere, you can set their value or define them wherever later in whatever order you really want. So that's kind of a weird one, and why I would kind of recommend getting away from the Arduino IDE if you're trying to do complicated code. So we'll get into alternatives in, I think, the slide after this one. So before we get there, Arduino libraries, like I mentioned before, you can write your own libraries, or you can use other people's ones. So they help you simplify what code you write and remove sources of bugs, because if you're using somebody else's library, hopefully they've already removed the bugs, and then that just means you can use it and assume it's working correctly. Only works if you have like really well-known libraries, but it's generally a decent assumption. But things they can do, they can interface with hardware. So basically they can talk over whatever communication to your sensor and say, set up the sensor, and then let you read values off of it really easily without you needing to like, no, I need to read this register and convert this register's value to another value. And they kind of just make it really easy, like sensor.read, and that's all you need to do, and it figures everything else out for you. You can use kind of plugins, which will add software features, like we'll talk about in a minute. You can use it to handle running code at 10 hertz, or you can make it so that you can have linked lists, or you can have all sorts of stuff you learn about in ECE classes or anything like that. If you want to add more software functionality, you can use them without having to write them yourself. And there's a ton of support for a ton of different I/O input-output devices and software features. Just Google literally anything Arduino library, you'll probably find something. So Google, GitHub are great. And then generally where I'd get libraries from is Adafruit or Adafruit and SparkFun, or well-known individuals, I'd say, or like repositories in GitHub that have a lot of people active on them, because those probably have fewer bugs, if any. So anybody have questions about Arduino libraries, what you could use them for, or anything like that? Okay. So we'll move on. So this is kind of the behind the scenes of how Arduino works. So it's a little bit complicated. I'm going to try to make it simple, but basically you can follow the graph on the right, but when your microcontroller Arduino turns on, it does the boot microcontroller stuff. So it sets itself up, it kind of figures out what is going on, make sure everything is like cleared and reset. And then after all that's done, then it actually runs your setup code. Once your setup code runs, it actually runs another loop, which is like the main update microcontroller loop. So this does everything from updating millis. So it says, okay, it's been enough time for millis to go up by 1, stuff like that. So that loop is running kind of in the background. You don't see it or know about it, but every time or every few times it runs, it'll call your loop. Your loop has all of your code that does all your robot stuff. Once that finishes, it goes back to the update microcontroller loop. And that, again, does things like updating millis and stuff like that. It's a bit more complicated than that, but generally you have this kind of loop here going between update microcontroller and loop. So your loop keeps running over and over, and the update microcontroller loop runs over and over and over. So this update microcontroller, or hardware loop as I call it here, just kind of make sure the microcontroller is happy and everything is going on correctly, making sure there's nothing kind of like getting forgotten about. So everything is going on, so the microcontroller is happy and everything's working correctly. So this is how it actually works. It's not actually your loop running in the background, or it's not just your loop running, it's your loop and this update microcontroller loop. And in this update microcontroller loop or hardware loop, it can run all this Arduino framework stuff. So you can have things like free RTOS, which we'll talk about in a second, which can run tasks at some frequency or in parallel-ish. So you don't need to worry about it in your loop. So instead of doing if millis is greater than whatever, like that first example I gave of the code, you can have the Arduino framework in this hardware loop kind of do that all for you. And you can have your own bits of code that'll just keep running in loops, and you can just add your own kind of loop functions by yourself without needing to deal with all these other things going on. So that brings me to the real-time operating system, which allows you to run multiple programs at the same time. So it's a bit more complicated, but we're going on the assumption that it's programs and that they're running at the same time. It's not exactly that, but for our purposes, that's close enough. These programs are called tasks. They can be given a priority level. So again, maybe making sure your motors are running with the right values at every given time is the most important. So you can give that a high priority. Maybe dealing with your battery voltage is a low priority, something like that. So these tasks can run once, or they can loop over and over and over, like I mentioned before, like creating your own loop functions. So you can use an infinite loop, like a while one loop. It'll behave exactly the same as your regular loop function that Arduino has for you. And these tasks are all managed by a scheduler, which determines which tasks run at any given time and how long they run for before the next task runs. And the best thing is the scheduler is written by other people and it runs in the background, so you don't need to worry about it. You just tell it, okay, I want to start the scheduler, and then all of your tasks will start running automatically, and you don't ever have to worry about, is millis greater than this value? We need to update this value. Is millis greater than this value? It can all just happen in the background and not in your code, most importantly. And so like the scheduler basically makes sure all tasks get enough time to run, no matter how many tasks you have, up until you basically run out of resources to run enough or run more. It just kind of schedules and organizes everything. So this is the more pre-made or more performant version of the millis example. I have to put the slide number in before I send the slides out, but this is that first example I showed. So instead of doing millis is greater than a value, you can just let this thing figure it out. And it makes your code a lot more readable because you get a whole nother function. You can have your void loop, which does stuff, but you can have like a void, like motor update loop, and that can do its own thing. And there can be completely separate, and it just makes your code easier to read and also faster. So why wouldn't you use it? Does anyone have questions about RTOS? This is a very, very complicated topic. I'm trying to get like a general understanding to you guys so you can kind of know that it exists. And again, I'll show more examples later. Okay. So I mentioned that Arduino IDE is kind of painful to use. So I'd recommend VS Code. Kurt and I have used this for a while, and it's probably the best thing you can do for Arduino programming. So you get VS Code with the link here. Again, the slides will be sent out so you can follow this later. Just download it. It's free. It's a pretty great IDE. Also, second bullet point is very important. Dark mode is very much required because it's just better. And then, yeah, so you can follow the steps for Platform IO after you install VS Code. So effectively what you're doing is just installing the extension. The link there gives you a full walkthrough for installing it. And then there's a quick start guide for Platform IO linked below if you wanted to kind of do more on your own beyond what I'm going to get into in this workshop. So slides will be sent out so you guys can follow through this all. So the reasons I would use VS Code and with Platform IO, it's powerful IDE. It does so much more than Arduino does. Supports dark mode. That's one of the main ones. And you get much faster compilation times. So the Arduino IDE is kind of slow. I'm pretty sure it's single threaded, and it doesn't really cache things. So generally it takes a long time to compile every single time, which is annoying. But VS Code is very configurable. You can make it cache anything or everything you want. It's much faster compiling. You can control how it compiles a lot more. And you can do more advanced things with VS Code if you want, like pre or post processing of your code. So for example, if you have HTML files, you can convert them to C++ compatible code. If you're running like a web server on an ESP32, you can write all the code in HTML and you get all the benefits of auto completion in a .html file. And then you can have it run whenever you compile, convert current state of those HTML files into C++ code, and then it just converts them automatically rather than you manually copying and pasting and formatting it all nicely. And you can generate code programmatically based on values you have or add. So if you want to like have a serial interface, like if you want to be able to control certain values, you can just add a value in like a Python script and it can generate the C++ code for you if you've written that to do so. And then when you upload it, it's just there's a new interface you can talk to over serial. Gives you a lot more control to do more advanced things like that. And then you can get real-time code warnings or errors in the bottom console, rather than when you compile, it'll tell you that everything's wrong in Arduino IDE. This one, whenever you type something wrong, it'll give you the red squiggly line and it'll give you warnings and errors in the bottom console to say, hey, line X on this file has some sort of issue. So those are the benefits. These are the tips on using Arduino for VS Code. So the main thing is the platform IO.ini file, which basically controls how everything works. So there's a couple links there that explain what all the file can do and kind of how it sets everything up. So most of it you don't really need to touch. It's just there if you want to change things. And it just kind of tells it how to work with like your project basically. So the main gotcha, I think, is this monitor speed thing. So this is just the serial monitor. By default, it's 9600 baud, but I generally use a bunch of other ones. So you got to put this monitor underscore speed equals in that file to tell it when you open the serial monitor, I want you to use whatever speed you say in serial.begin. It just has to match. A couple other useful things, like I mentioned, you can use like a Python script that runs before compiling to convert HTML to a header file for C++ compilation. You can do things like if you're working on ESP32, the serial monitor can automatically decode errors and tell you what line issues are on. If you have like a runtime crash, tons of different things. You can do a packages directory, which will basically tell it you have your own code for controlling how the actual microcontroller works on the low level when you're working with like a custom PCB, tons of different things like that. So you don't really need to get into most of them. So they're just there. Again, just wanted to mention it so you're aware of it so that you can know that it's there if you ever want to delve into more advanced things in VS Code with Platform IO. Okay, and then so the tips and tricks, there's a whole tips and tricks guide for VS Code linked there, but these are the main ones that I use. Multi-line editing, you can hold Shift plus Alt while you're dragging your cursor to select multiple lines of code, and you can change, like if you need to change like the name of something, you can change it in a bunch of places, all line by line, really easily. Happens more often than I thought it would have, but it's a fairly useful feature. You can right-click on a function or a variable and see what calls the function, what functions use the variable across all of your files you have. You can search with Control F, obviously, but you can search across all of your files. Some of your files, you can use regular expressions if you know what those are to search and look for more specific things. There's just tons of different things you can do with that. And you can use extensions to add features like just like region folding. So you can kind of say this region of code is all for monitoring the motor, and then you can collapse it and say there's like a little plus button that says like motor code or something like that. And then you can click it to expand. Tons of different things you can do. You can configure the IDE exactly how you want it. Auto save, auto formatting, tabs versus spaces, end of line conversion, tons and tons and tons of different stuff. You have side-by-side editors to have like your main.cpp code on the left, and then you can have like a library example on the right, and you can just drag the window to the left or the right, the top or the bottom, whatever you want to do. Makes it really easy to have multiple files open at the same time referencing each other. So I think at this point, I'm going to say, like, if anyone wants to leave, they're free to. Otherwise, I'm going to walk through an example for using PackBot as an example to walk through using Platform.io and setting up an example and writing all of like the framework of the code. So just jump to the end. If people want to get their active membership point before leaving, feel free to scan the QR code and let me send the link in the chat so you guys can click on that. But I'm going to go over the whole example if people want me to, and then we can probably finish up around 6 like planned, but if people need to leave, that's perfectly fine by me. So anyone have any questions at this point? I know I talked about a lot of stuff and my voice is definitely feeling it. So okay. I think we'll wait for like a minute or two to let people click the link, or I guess the link's going to stay there. I can just move back to the other slides. So no problem, Jesse. Okay, so yeah, I guess looks like participants are staying mostly the same. So we're going to go through an example of PackBot. Like I mentioned, this is the code that would go on the ESP32. So basically the hardware of the PackBot has Raspberry Pi, which determines what to do at a high level, like drive forward, drive backwards, turn right, turn left, stuff like that. The ESP32 is the main hardware controller that actually talks to the motor drivers, the IMU. It has some buttons on it. So it kind of decides what to do actually, like piece by piece. So it talks to the motor driver to control the motors to move 2 millimeters left, 2 millimeters on the right, whichever one. You can use the IMU to monitor rotation or movement it has. You can take in buttons to see, oh, thanks for coming, Annika. If you have buttons to control how it can behave, like if you want to run one subroutine or if you want it to do a different one or a test mode or something like that. So this is how it's connected up. So the ESP32 has a serial UART with the Raspberry Pi. It has a serial UART with the motor driver on the left, a serial UART with the one on the right. It uses I2C to talk to the BNO055 IMU and a digital pin for button 0 and button 1. So kind of the steps we're going to go through is to create a Platform.io project, determine what tasks we need, create the loops using FreeRTOS, write out what each task needs to do, and then writing all the setup code to link these tasks and interrupts if we want to actually kind of bring everything together. And then this is going to be just an overview of what needs to be written. There's obviously a bit more if you want to actually do more things with it, if you want to actually link it together and get commands moving from one to the other. But this is just going to be kind of how you generally set the code up. And like I mentioned, the workshop is going to be plenty long enough already. And I think that's definitely true at this point. So I think we can get started. Let me share VS Code. Okay. So open up Platform.io. You guys can see my screen, right? Or VS Code, that is. Okay. So once you open up Platform IO, you can go into extensions over here on the left, which is the 3 boxes with the 4th one kind of coming in. And then you just search for Platform IO. And then the first one, IDE, you can click the install button, close and reopen VS Code, and you'll get this Platform IO option on the right. And then you can click open to open the home. And this is what you've got. So you can see your recent projects you're working on. You can look at your libraries you are using currently. I have a lot that need updates apparently. You can add boards. So main one would be ESP32. So you can just find the boards, like Adafruit Feather is the one I use most of the time. So you just want to make sure that one's available here. Otherwise, you can download it. You can get platforms. So like, again, ESP32 or Espressif 32, you can install that. So it lets you kind of manage everything pretty similar to how the Arduino IDE does. So we'll start a new project though. So this is going to be workshop test. We're going to use an ESP32 board. We'll use the Feather here. We're going to use the Arduino framework. And then I'm just going to put this in a folder that I know. Oh, I'm not on my desktop. It's going to go in PCB Workshop then. So it's going to get everything set up for your project, all of the files kind of set up, the platformio.ini file, like I mentioned before. I don't know why. Okay, well, apparently Norton is not happy with that. So we're just going to put in the default location and hope it works. Okay. So let me remove this folder. So when you create a project, this is what it'll look like. It'll just be blank screen. You have your platform.ini file, like I mentioned here. So first, I'm going to grab that gotcha thing. So we can just make sure we have that because I've forgotten that several times. Because if you don't include this, it defaults to like 9600 baud, which is not what I use for anything. So you can open up source. Here's your main, which looks exactly like an Arduino file, except it keeps this include at the top. Arduino includes that automatically, but most compilers don't include things automatically like that. So that's just there. You can leave that alone. So the first thing we should do is go to this. So we need to determine what tasks we need. So if we look at this, we probably want a communication task for the Raspberry Pi, one for the motor drivers, one for the IMU, and the buttons we can do an interrupt for, like I mentioned before. So just drag this over to this side. And I'm going to show this. Okay, so if we come in here, we want to do something like Raspberry Pi serial. We want motor driver serial. We want an IMU. And then we're going to do that. So that covers what tasks we need. So then we can create the task loops and write out what each task is responsible for. So one thing is just Google FreeRTOS Arduino, maybe. Okay, well, I know the format. I don't see one that I normally reference, but the format is basically, it's a void function because it returns nothing. This is Pi serial is a name, and then it takes a void pointer, so void asterisk, parameter. You basically don't need to worry about that. You just need to have this sort of structure, void, whatever you want to name it, void asterisk, and then just some name. So we're going to do that for the Pi, the serial, and the IMU. Okay. And then we need to write out what each task is responsible for. So we'll say read in serial data, and then maybe we'll have it. We don't need to go into too much depth. I guess we'll just say like that one just reads it in. This one writes out serial data. Should rename these motor serial and IMU comms. We'll say I2C because that's what it is. So it's going to write out serial data. This one will be like reads in IMU object values. And then we want two functions for the interrupts. So the format is given on the Arduino reference page, but basically it's just going to be like button 0 int is just what I'm going to name it. It takes no arguments, so it's just open close parenthesis, curly braces to say this is a function. And then this one's just going to say like serial prints out something. I don't know. And then the other one can do something else. I don't know. But you can put whatever code you want in here. And so this is basically what each task needs to do. So now we need to write the code in setup to link all these tasks and interrupts. So we can do the interrupt first. Let me see. Probably find the reference somewhere. There it is. So these are all the functions. It has even more than I mentioned, but the main ones are also here. So here's interrupts, attach interrupt. So do they have an example? Yes. So here's the syntax for it, what you actually need to call. So we're going to do attach interrupt, digital pin to interrupt. And we're just going to say this is pin 3 because there's no actual hardware to do this on. So this ISR is what we actually called the function. So we're going to call this button 0 int. And then we have a couple options down here. You can see there is low. Whenever the pin goes low, we want to call it. Whenever the pin changes, we can call this function. Whenever it rises, whenever it falls. It's a ton of different options. We'll just say whenever it changes. So you just type change and then a semicolon at the end. And that is the entire thing. So whenever pin 3 changes from high to low, it will call this code. Nothing else needs to be done for this. 1 second. So you don't need to do anything in your loop to check if it's high or low. All you need to do is just this piece. And then we'll do the exact same thing for pin 4 will be button 1, but we'll say when this is falling. So whenever it's a high and then it goes down to a low, like when you push in a button, it will fall and then it will call this code. So the next thing we need to do is set up all of these to be created. X task create is the syntax. Again, just Googling FreeRTOS or like ESP32 RTOS will give you a ton of examples for it. So there's a couple different options. The main two are these at the top. You can do X task create, which will work in pretty much any microcontroller, an ESP32. I think they work in the Arduino Uno Mega, that stuff. You can do it in an AT-SAMD, pretty much anything. And this is the general one that you use. If you use pin to core, you need to have a multi-core processor. So the ESP32 is multi-core. So we could say, I want core 0 to handle the communication with the Pi, and core 1 to handle communication with the motors if I want to. For now, we're just going to go with the regular task create, which just lets us set up the loops like I mentioned. So this is all kind of a lot of text, but really all this is the task function. This is the function of the task. So we'll copy and paste Pi serial. Next thing underlined is the name of the task, basically. You can give it literally anything. You can say this is Pi serial task. Next one highlighted is the stack depth. This one is kind of tricky. So this is basically how much memory you're giving the task. So it kind of depends how much code is in the task, but generally, if you have like an ESP32 or an AT-SAMD, you can start out with pretty big numbers like 2048. Powers of 2 are nicer, but you can do any number. And then, so if you have errors, it will give you an error on serial saying like keep memory, something like that. It'll say memory in the error, and you can tweak it up. Again, if you have weird issues, let me know. Using this, I can help debug it because I've done this quite a few times. So the next one is this parameter. So this thing right here is what this thing is going to be. So if you wanted to pass it like a pointer to, or if you wanted to just pass it like a string like high, then when this code runs, this value is high. But since we don't really need that, we can just say null, which is equal to 0. It just says there's nothing here, don't worry about it. There's the priority, so you can do like just a number. There's also, I'm forgetting the name of it, but that's the best thing about Google. So you have FreeR2S priorities. What are the names? This is the format, so you can do TSK idle priority is, well, the lowest priority. There is a ton of different priorities you can use, so you can do that, or you can just use numbers. I normally just use like 1 because it's the default one. And then finally, you have this task handle, which is kind of a complicated thing. You don't really need it for just getting another loop running, so you can just put it to null, say there is none. And this is all we need. So we set up the 2 buttons, so whenever they get clicked, they call the code. And then we create a task for Pi serial, which will run with a certain name and with certain amounts of memory. And then we can just copy and paste this a couple times. We have motor serial, which can just change. We'll just change this piece to motor serial. It can keep the same amount of memory. That's fine, and the same priority. And then IMU, we can do the same thing here. We just copy and paste the function, and we'll just say like, this is the IMU task. And maybe this one needs a little bit less memory or something. So then we have all of our tasks set up. And then at the end, we need vtask start scheduler. Also, one of the best features about like using an actual IDE is it recommends what it might be. Like I thought it was scheduler start, but it's actually vtask start scheduler. So I can just click on that, and then I click this. And once this line of code starts running, all of these tasks will start running automatically. And I don't have to worry about anything. I can leave nothing in this loop. It can just be empty and everything else will run. So if we want these tasks to loop, we need to make them loop. So by default, when the task runs, it will call the code. And once it returns, it's done. It throws all of it away. But we want it to continually loop. So what we do is we can do a while loop, like I mentioned before. And then we just do this. So 1 is always true. 1 is always equal to 1. So this will never end. This will just keep looping. This is effectively the same as this being like a our void loop function down here, but we have this one and void loop. And we can do the same thing for all of these. These can each just loop over and over forever. Forever. So now we have someplace we can write code for serial.read. We can do a bunch of different things like that. And we don't need to worry about making sure it all has enough time to process or anything like that. It'll manage all of that in the background for us. So one last thing we need to do is the hardware setup. So we need to do serial.begin to tell it what baud rate or how fast the communication needs to happen. So there's one serial. I'm going to put a comment here just to say this is serial used for Raspberry Pi. Serial1.begin. We'll say this one runs at a different speed. Serial used for motor driver 1. Serial2.begin, 38400. So we have our serial objects created so we can actually communicate with them now and talk about them or send text on them. So up here in Pi serial, we can do something like while serial.available to see if there is any text available. We can do something like character A equals this. So whenever there's data available on this serial port, we can read it into this variable, and then we can process it however we want to. So we can say, is this variable A, is it like a command character, like is it a C, or however you want to control everything, make communication happen, you can kind of check, is this, you can read in multiple characters, is it like a word like move or whatever you want to do. You can check that here. And when it's true, you can do different things, like you can say, okay, now we need to tell the motor drivers to move, things like that. So we can do the same thing over here. If we need to read in the motor driver 1, and then we have motor driver 2 we'll need to read into, so we can just copy and paste it really. So whenever they're available or they have data for us on the serial port, we'll read it in, we can parse it, we can do whatever we want to do with it. We can say, okay, it said it's done with that. What's the next thing we need to tell it to do? However you want to organize your code like that. And then here we wanted to serial print out something, so we can just do serial.print line something. So this will just tell the Raspberry Pi something, or this will tell it else, whatever we want to do. And I think like my favorite thing about all of this is that void loop is empty. It's really easy to see, like you don't have all these things in the other examples, like there's an if statement and then a bunch of code and then another if statement and then a bunch of code. It's just, here's one thing. This happens whenever an interrupt for this button happens. This happens whenever the other button gets clicked. This happens over and over by itself. You don't need to worry about it at all, because that's what this task creation and start scheduler does for you. Like once you learn this syntax, you can just create loops like this, which makes it really easy to say, like, here is where all of the IMU code lives. This is where everything I do, like imu.get. Like I can read in the IMU values really easily there, and I don't need to worry about, like, maybe this get will take 100 milliseconds to read, but I don't care, because the scheduler, which is my favorite thing about all this, will say, okay, while you're running whatever, all these other loops will continue to run in the background. It'll just say, okay, IMU, you're on pause. We're going to wait for you to do your thing. And all these other loops will get to run at the same time. So you don't have these issues where if you had your everything in loop and then you did like well, I needed to delay 100 milliseconds here. Now all my other tasks will be okay. So even though I'm waiting here, it's not pausing everything. It's just saying this loop is on pause. Everything else can still happen. Anybody have questions about that? Because this is quite a lot. Rather, what do you guys have questions about? Also, don't be scared of this because there's a lot of syntax and stuff here, but really once you know C or C++, or once you learn like that these things exist and start using them, it gets much, much easier to understand kind of how to do it. It kind of just, it's a big learning curve, but it becomes really, really, really useful. Okay. But I'll send this code out with the other code examples with the slides and everything. So if anyone has any questions, feel free to ask me now, or send me a message on Discord after the fact would be great too. Okay. I think that's everything I had planned for you guys. So if you guys haven't already, there's the link for getting your active membership point. It's also in the chat. I can send that again. So, but yeah, thank you guys for coming.